Hello, my name is Roman. So to begin, we need to begin this, how we will use the Lewis relation in an energy balance um, with a wet and dry bulb for the relative humidity, and then we'll explain the relationship between the adiabatic saturation temperature and the wet bulb temperature, and then we will derive the equations for the differential equations for the mole fraction of water vapor in the air and the temperature of the air and water in a cooling tower. Now, with that information, we will then solve the differential equations derived for a 20-meter tall cooling tower where the air-water heat transfer coefficient is 10 watts per meter squared Kelvin, specific area of 5 meters squared over meters cubed. Hot water enters from the top at 70 degrees Celsius with a flow rate of 0.5 kilograms per meter squared second. And the air enters from the bottom with a velocity of 5 meters per second at a temperature and relative humidity of 25 degrees Celsius and 50% respectively. Then we will plot the water temperature, air temperature, and the water partial pressure as a function of position in the cooling tower. So let's begin. So to start, we need to define the Lewis equation. So when we're starting to define the Lewis equation, we start off with the Nusselt's number, which is H multiplied by some density over the thermal conductivity K. And then we have the Sherwood number, which is equal to the mass transfer coefficient multiplied by some density over the diffusivity constant. Now, if we look at this and we look at the underlying driving forces of the two equations, we see the mass transfer and the presence of convection have a identical form. It's always some diffusivity multiplied by some derivative of a concentration and a thermal energy concentration. In this case, it is actually the molar mass concentration. So we begin with multiplying A by some Reynolds number raised to the power B, then multiplied by the Schmidt's number raised to some letter C. Now we do that for both equations. However, the Sherwood's number is going to be multiplied, the Nusselt's number is not multiplied by the Sherwood number, it's actually multiplied by the Pradle's number. And the Sherwood number is multiplied by the Schmidt's number. Now, so what happens is that the coefficients are actually identical. And then we have the Nusselt's number, and you have the Pradle's number, and if we raise that to some power C, like I said before, and then to determine these coefficients, we need some experimental data. In this case, the mass transfer, we have the Schmidt's number, and now the Pradle's number, which is equal to the velocity over the density multiplied by the thermal diffusivity. And then we also have the Schmidt's number, which is equal to the kinematic diffusivity divided by the density multiplied by the diffusivity coefficient, and we have the So then we will divide these two numbers, the Sherwood and Nusselt's number, and we'll break those down into their simplest forms, which will be the mass transfer coefficient multiplied by the thermal conductivity divided by the density, or the diffusivity coefficient multiplied by H. Now, if we look very closely, notice that these actually simplify to a simpler term, which will be alpha over DAB raised to some power C. Now, this number, if we look closely, we'll actually realize that this number is the Lewis number. The Lewis number. And then we could also even write this out as K over rho Cp multiplied by the diffusivity. Now, when we're talking about the Lewis equation, and we think about it with moist water or humid air, or moist air, let me say that, the Lewis number is actually equal to 1. So now, if we analyze the Lewis number, K over the diffusivity coefficient is equal to rho Cp, the density times the heat capacity. Now, if we remember what the Sherwood over Nusselt's number is, we'll see that it's approximately 1, and that K over DAB is approximately 1. I'm sorry, let me write over here. K over DAB is equal to 1 over rho Cp. And this is the Lewis relation. Now that we've defined the Lewis equation, we want to determine the humidity within the air for a wet dry bulb experiment, and we'll be doing this with an energy balance. So to start off, we start off with a mass transfer coefficient. Mass transfer coefficient multiplied by the concentration at the surface minus the concentration from far away. Now, to get our desired moles per meter squared second, we need to multiply this function by the heat of vaporization, lambda. Now if we apply heat to water from the air, we know that the air is hotter than the temperature at the surface of the water. So we do H times the temperature times the temperature away from the surface minus the temperature at the surface. Now this T right here is the heat flux, and it is going from the air to the surface of whatever, in this case, is the wet bulb. So to explain the wet bulb experiment, we've talked about it previously in class. You get a thermometer and you take the air temperature, and then next you get some rag and you wrap it around the bulb of this thermometer, and you spin it around in a centrifugal with centrifugal force very fast. Now this experiment will allow you to determine the humidity, because the heat or the rate of vaporization on the thermometer will allow you to determine the humidity, because the heat leaving and the water evaporating will drop the temperature of the thermometer, allowing you to determine the heat of the humidity within the air. So when we look at this equation, we'll notice that there is a Lewis relationship here. we have a H and a KC. And what we know is that if we have those on each side of the equation, that we can break down the Lewis equation and place it in. So on this side, we will have lambda for the, we'll break down the concentration of the liquid into the partial pressures. So the partial pressure of water at the surface over RT, and the partial pressure of the surroundings over RT, and then we will convert that H into rho Cp, rho, squeeze that in, and then we have the temperature from the surroundings minus the temperature at the surface. So for the temperature with the partial pressure and the temperature from the surroundings and the temperature at the surface, we know that there won't be too much of a fluctuation within those temperatures. So we'll say that the temperature of the surroundings and the temperature average, which is the over RT, and the temperature at the surface are all roughly about the same, which cancels out R over T, and then we're left with lambda, partial pressure of water at the surface minus the partial pressure of water away from the surface is equal to the total pressure, Cp times the temperature away from the surface. Now we want to incorporate this as an energy balance. So then we will plug in the molecular weight into this function. So then we're left with lambda, the molecular weight of water, multiplied by the partial pressure of water at the surface times the partial pressure of water from the surroundings, multiplied by the pressure, which is equal to the total pressure of the system, multiplied by Cp, and the surface, or the temperature away from the surface and the temperature at the surface. Now you'll notice, I don't think I mentioned this earlier, rho can be converted into the total pressure of the system, and now that is all we have for converting this into a energy balance for the Lewis relation. So now that we have gone over the Lewis relation and the Lewis relation with respect to energy balance, we're going to apply that knowledge to a wet bulb experiment-like situation, where we will start off with an infinitely long tube that is insulated. Now this tube is insulated because this problem will cover an adiabatic saturation temperature. Now adiabatic means that this tube is well insulated, meaning that there will be no energy entering or exiting the system. Now when we look at this tube, the water here is constantly being supplied at a temperature TW. Now the water is continuously being added through this tube. It is not sitting stagnant. We will also say that this water has some saturated partial pressure of water here at temperature TW. And then we want to say that we have a mass flow rate entering the tube of air being supplied through the system, and then the mass flow rate going through the system will become saturated with water. Because this tube is infinitely long, the evaporation of water will saturate the air into the system. So we know that this will be so we know that the partial pressure exiting the system will eventually be the partial pressure of the water at TW. Now we know we're giving some mass flow rate of air through the system, and we're going to say it starts at some temperature T in and is being supplied at a certain pressure, and that the pressure changes when it comes out, and the temperature will change when it comes out. Now, to start applying the knowledge of the energy balance, we need to start thinking that the temperature changing will have a difference in energy, meaning that we need to think of this problem like an enthalpy problem. Now, to start off with an enthalpy problem for this type of experiment, we want to say that the experiment is steady state, so that the enthalpy in is equal to the enthalpy out. Now, we know that we are talking about a change in temperature, so we need to have our enthalpy in having some sort of heat capacity. And the air going in that we've talked about is the mass flow rate. Now this is the enthalpy in, so this heat capacity is going to be multiplied by T in, and is going to be supplied going to be added to the heat of vaporization, because we know that the air going into the system is going to be dry and it has eventually become moist and saturated. So we know that we're going to have to apply some sort of heat of vaporization. Now, looking at this tube, we know that we will eventually have to have some partial pressure of water entering the system over the gas constant R, T, multiplied by the molecular weight of water. Now we need to, so we know that our units are kilograms per second for the mass flow rate. Our heat capacity is joules per kilogram Kelvin. And we have our heat capacity, we have our heat of vaporization, which gives us joules per mole. And we know that we need to end the equation with excuse me, of cubic meters. So we need to multiply this part of the equation by its inverse, so that we will end up with meters cubed. Now, when we multiply this by its inverse, we will have to equate the total pressure in this case, so that we can negate the partial pressure in. And we will multiply this by the average molecular weight, because we know that the molecular weight will be a mixture of dry and air. Now, before I simplify this, we're going to talk about the enthalpy out. Zoom out. Now, the enthalpy out is going to be very similar to the enthalpy in. We know that we have a mass flow rate going through the system, and we know that we similarly have a heat capacity multiplied by the temperature out. Now, we also, again, have lambda, which is the heat of vaporization. However, since we know that the gas leaving the system is going to be saturated and equaling to the partial pressure saturation of the water, we do not need to account for the change within the mixture of the gas. So we can essentially just say that the enthalpy out is lambda, or the heat of vaporization, is equal to the partial pressure of water at the saturation point of TW, because it is fully saturated within an infinite tube, times the molecular weight of water over the total pressure multiplied by the molecular average weight. Now we're going to equate these two, because we said it is steady state. We have enthalpy in is equal to enthalpy out. Molecular weight of air entering the system at a heat capacity temperature in, heat of vaporization multiplied by the partial pressure of water going in, multiplied by the molecular weight of water over the gas constant times the temperature. Then we have the gas constant times the temperature times the total pressure times the molecular average weight. And this is equal to the enthalpy out, which is the molar flow rate of air times Cp, heated capacity, of the temperature out plus lambda, the heat of vaporization, times the saturation, partial pressure saturation of the gas at the end of the tube multiplied by the molecular weight of water divided by the partial or the total pressure of the system times the average molecular weight of the mixed gas. Now, if we simplify this problem, we'll actually realize that this equation is a Lewis relation. So when we simplify this problem and we bring over the lambda, we see that we have lambda, the heat of vaporization multiplied by the molecular weight divided by the total pressure of the system times the molecular average weight, partial pressure of the gas entering the system minus the water, the partial pressure of water at the out, or at the end of the tube, sorry, is equal to the total pressure of the system times the heat capacity times the temperature out minus the temperature in. And if we look at this, this is similar to the Lewis relationship, that is lambda times the partial pressure of water at the surface minus the partial pressure of water away from the surface, which is equal to the total pressure, which is similar to rho, times the heat capacity times the change in the temperature from away from the surface minus the temperature at the surface. And as you can see by these two equations, they're similar, and that is the relation of the Lewis relation to an adiabatic saturation temperature to relate the humidity to the wet-dry heat bulb experiment.